Okay, in the last video we looked at the trends in solubilities of sulphates and hydroxides. Okay, with the sulphates in blue here, right, we have got the magnesium sulfate is pretty soluble and barium sulfate very insoluble. So it decreases as you go down the group. And with the green ones here, the hydroxides, you get the opposite trend. Magnesium hydroxide very insoluble, barium hydroxide soluble. Okay, there's a nice little experiment demonstration you can just show that's the point. Well, what we've got here is I've got solutions of magnesium chloride and calcium chloride, strontium chloride, barium chloride, all the same concentration. Let's say you make that 0.5 mole per decimeter cubed. And then here's a pipette. This is a pipette, obviously, in case you're wondering what it was. And you put in the pipette, let's put in a solution containing sulfate ions. Okay, so that, e.g., you could, the most convenient thing probably would be you could use 1 mole per decimeter cubed sulfuric acid, or you could use copper sulfate. We always have that hanging around. And right, so what you do is you add a drop of that into these. Now let's think about the barium first of all. Right, you add, like, I'll do this right. You add 1 drop into the barium chloride, and you will immediately get a white precipitate. And the precipitate would be a barium sulfate. And you're going to precipitate even if you had 1 drop, because barium sulfate is very insoluble. If you did it with the strontium chloride, you might be able to, the first drop you wouldn't see a precipitate, because strontium sulfate is a little tiny bit soluble. So what you could probably get away with 2 or 3 drops, and then when you added the 4th drops, let's say 4 drops, you would get a precipitate then of strontium sulfate. And then when you come to the calcium, calcium sulfate is sparingly soluble. So you might be able to add, like, say, 15 drops of your sulfate solution before you got a precipitate. And then with the magnesium, well, you won't get a precipitate probably. No precipitate, because magnesium sulfate is pretty soluble, so it's not going to precipitate out. So you get this nice trend. You can add more drops as you go down the group. Right, you can repeat this experiment, and so I'm going to rub that out, and I'm going to do it in green now because that's the hydroxide. So I'm going to get rid of all of that, and this time we're not going to add drops of something containing sulfate ions. We're going to add drops of a solution containing hydroxide ions, and there's only really one choice for that. So OH minus ions in solution. You would almost certainly use sodium hydroxide for that, wouldn't you? Potassium hydroxide is also soluble. All the other hydroxides are insoluble, so you wouldn't use them. So add drops. Let's see. Now, if you add it to magnesium, you'd probably get away with adding 3 drops, because magnesium hydroxide is pretty insoluble. You get a precipitate then of magnesium hydroxide. Now, calcium hydroxide is more soluble. Calcium hydroxide is lime water, and I think you can make a solution of lime water, saturated solution of lime water is about like 0.1 mole per decimeter cubed, so it's reasonably soluble. So you might have to add, say, 15 drops of sodium hydroxide before you got a precipitate of calcium hydroxide, until you exceeded its solubility and it came out a solution. The strontium you get away with, like, you might be able to add 30 drops or something like that, and then the barium you can carry on adding it and no precipitate, because barium hydroxide here is pretty soluble. So it's a good demonstration of the change in solubilities as you go down, as you go down the down group 2. Though this is going to be the last video on group 2. It's a pretty short topic. There's just a couple of odds and ends to tie up which I haven't mentioned. One of them is, right, magnesium used in titanium extraction. So titanium is quite a hard metal to extract, and you end up making a titanium chloride, TiCl4, which is actually a liquid. It's a covalent liquid. It's a covalent molecule. It's not ionic. And you add magnesium to that, and you get a displacement reaction, because magnesium is pretty reactive, and you get titanium metal and magnesium chloride. So it does, one line in the specification says you need to know that. The other throwaway line in the specification is the use of calcium oxide in flue gas cleaning. Right. So calcium oxide, which you get from limestone, in a power station, any SO2 which is made when you're burning the coal, which don't burn much coal in this country anymore, but any SO2 which is made, right, that would cause acid rain. That reacts with the calcium oxide to form calcium sulphate solid, so it prevents this gas getting into the atmosphere causing acid rain. So there's just those two little throwaway bits in the spec that I thought I should mention before we finished up group 2.